Thank you very much for the nice introduction, and thank you all for being here. As was mentioned, I'm local, so I didn't have to transport myself too far, to use another transport pun. So today, I wanted to talk a little bit about conditional simulation to follow up on the talk that we heard yesterday by Franca on the subject, and provide a methodology to do conditional simulation using entropic optimal transport. And before I get started, so I just wanted to acknowledge my collaborators on this work. So this is joint work with Aram Palladian at Yale, Michael Brennan and Yusuf Marzouk from MIT, and John Niles-Weed from NYU. And what I'm going to cover today is published in AI Stats earlier this year, and it can also be found on the archive. And I'm very happy to share that offline with all of you. So to get started, what I wanted to do is to motivate the conditional sampling problem with two applications. The first is one of generative modeling. And if you'll allow me to say among friends, I really believe that in generative modeling, all the interesting applications are really conditional sampling ones, where typically what you have is a model that can generate structured objects like images. And really what we want to do is to use these models to sample certain types of images given some user input. So we want to imagine what a skateboarder in California would look like, at least based on all the data that we've seen so far, or maybe what a large aircraft taking off could look like. In this case, maybe even imagine that it has 3 engines on its right wing if you look closely. What we ideally would like to do is to build a model that can generate these kinds of images given not just maybe some prompts that we've seen before and that we've trained these models on, but on brand new prompts. The second application is one of inverse problems. So this is kind of closer to my heart and a lot of what I've done in the past. So here the problem is that we typically have some unknown state or parameter, and I'll start now introducing some notation for the rest of the talk. We'll denote this parameter by x. We might have some forward model that maps this parameter to some observation that we'll call y. You can think of this forward model as for instance, as Franca mentioned yesterday, maybe we have to solve some expensive P to E to predict, given the state of the weather or the atmosphere today, what it might be like tomorrow, and get some predictions of the temperature on some field. And ideally, what we'd like to do in inverse problems is, given that observation, try to infer the state or parameter x, and as well as the uncertainty in the inner estimate. And this is typically done by sampling what's known as the posterior distribution. So here, and for the talk, we're going to always denote these targets by mu. So mu of x given an observation y star, which is related to some prior that we know on the state and some likelihood that describes how the state is related to our observation. And this is applications. We mentioned numerical weather prediction, more broadly in the geosciences, pharmacology, medical imaging, and many others. Now, the class of sampling problems I want to focus on are ones where we have some challenges, and these are just a few of the ones that appear in practice. The first is that I'm interested in problems where the prior is not known. So these, in the context of, for instance, these image sampling problems, the prior is the prior over natural images. There's no analytical form for that distribution. The second is settings where the model that maps our states to our observations is also not tractable to evaluate. So maybe using, again, that application of sampling images, this function would be one that would take an image to a caption that then we want to condition on. But that process of captioning an image, it's also something that maybe we can build a computer model that will do that, but we can't really write down what the conditional density for the captions given the images would be. And of course, we're interested in sampling very high resolution images. So we're dealing with very high dimensional states and observations. And so in this setting, these are problems where you can't really rely on traditional methods. All you can assume that you can do is you can sample from sample some states xi from its prior distribution. You can sample typical images. You can sample captions given for that image. So you might have a human that might annotate an image and give you a caption. And so together these give us samples of the joint distribution of images and text prompts, or samples from this joint distribution of x and y that I'll call mu of x and y. And what we want to do is, given these samples, come up with a way to sample conditionals, ideally conditionals for x given some y star that we have not seen before. So a brand new text prompt that we haven't seen. And this is also broadly known as the problem of simulation-based inference, also known as approximate Bayesian computation, depending on the community that one comes from. So in the talk today, I want to discuss a methodology to do this with some statistical guarantees. I'll do this in 5 parts. So we'll start off by just talking about and reviewing the construction of maps that allow us to do this. Then we'll introduce a non-parametric estimator based on entropic transport. We'll provide some results on the analysis, and then I'll just show a few numerical results and conclude. So just to get started, so we're the setting of that we're going to use to solve this is we're going to look for a transport map that is going to ideally push some known reference distribution that we're going to choose. We'll call it rho to our conditional, and it's going to have to depend on the observation that we want to condition on y star. And we're in settings, like we mentioned, that we don't have samples from this target that we care about. The source is going to be always something that we pick, but the target is we don't have. All we have is samples of this joint distribution. So how do we learn these maps without our target samples? And the idea is that we're going to build a map from some source to this joint distribution of states and observation that we do get to sample. That also gives us a transport that allows us to sample conditionals. And this is, we already heard one such construction of these maps yesterday. Just to sort of generalize that and make some connections to that picture. So we're going to consider a map T that's going to take product measure rho on 2 variables, I'll call Z1 and Z2, to the joint measure of y and x with the following what we call block triangular structure, meaning that we have 2 components in this map. One that we'll call Ty, it maps Z1 to the observation space Y, and another map Tx that maps both of our source inputs to the X space. And what one can fairly easily show is that if T pushes forward rho to mu, then Ty will push forward the first part of the reference, rho of Z1, to the marginal of the data mu of Y. And the second part of the map, Tx, will push forward rho of Z2 for each Z1 to the conditional, the remaining part of the target, mu of X given Y. And we discussed yesterday about how this really, what you're going to, this second component, what it conditions on is related to the first component. And so in practice, you need this invertibility of the first component in order to condition on a particular y. One thing I want to highlight, just because this question came up yesterday, is you really have choice over the source measure. Rho, you get to pick it. So you can pick it to be anything. You can, in fact, pick the source measure to be the product measure of the observations and some source that you get, like a standard Gaussian. And in that case, actually, the first component, all it's going to do is map the marginal of y to the marginal of y. So you could just take one map to be the identity. And then this second component is really just explicitly a function of the variable that you want to condition on, and maps from the Gaussian, let's say, rho of z2 to the conditional of x given y. In some cases, you can even take rho of z2 to just be the prior. So then you really have this prior to posterior map as we discussed yesterday. So the idea is, as algorithms for conditional sampling, is you sample this joint distribution of x and y, and then given a new observation y star, you plug that into the map and evaluate this second component at samples from the source. You get new samples from the conditional. And typically these maps, the way that they're found is using variational approaches. So you choose some statistical divergence, call it D here. And we say that we want to find this map that pushes forward rho to the target mu. So as an example, one can take things like the KL, like we heard yesterday, but many other choices. And if you have samples from mu, we can approximate the expectations in these losses with our joint samples and use them to build estimators for these conditionals. In fact, for any conditional, so you can take, for instance, some 2D joint distribution like this banana, look at different slices of this, which correspond to different conditionals if the y-axis is the variable you want to condition on, and learn a map that can sample from any one of these conditional distributions. And this has really been the focus of most modern machine learning approaches to conditional sampling that can solve tasks like image in-painting problems, where you take an image, you remove the center part of the image, you observe only the outside of the image, and then you want to complete the image. And for instance, in this top row, you'll have models that can sample images like a 7 or a 9, which is consistent with the fact that when you just see the outside of this image, you can have many digits that are consistent with that image. And I don't want to just overview all of these methods. I mean, the literature just grows day by day. The citation count also exponentially faster. But there's many approaches based on normalizing flows, GANs, recently diffusion models that do this. But they all require a huge amount of investment, whether that's student time, whether that's just computing, in order to actually come up with the parameters that can actually solve some of these complex tasks. They often need very specialized neural network architectures, and coming up with the optimal parameters that achieve the SOTA, state-of-the-art results, as is often the term used in machine learning. A quick question? Yes. Yes, of course. By traditional conditional density estimation, or maybe you're thinking of like just kernel density estimation methods, and that can still amortize the density estimator to any new observation. I mean, it's a great question. A lot of the results actually, so the short answer is K to E methods in high dimensions. You're going to pay the cursive dimensionality typically. Theoretically, a lot of these methods also, at least what can be shown is that they still also have the same issues. But in practice, they do work for very high resolution problems. So there is a gap there. Thanks for the question. In this work, what we wanted to do is just come up with a methodology that can provide an estimator for these types of maps with that doesn't require tuning an unreasonable number of parameters, so just 1 or 2 parameters, and that still comes with some guarantees on the sample size required to estimate these maps. What is our proposal here. That is to say that the particular map first that we're going to use is one based on optimal transport. In particular, one map, often it's in a lot of work by Carlet, he called this the conditional Brenier map. This is the map that is a function of two variables, y and x. It's a map that is the gradient of a convex function with respect to x, but parameterized by y, and that pushes forward some source to this conditional of x given y. And what we're going to rely on is a result also of Carlier and collaborators that says that these OT maps, you can actually find them as a limit of a sequence of OT problems on the joint space of x and y. So this is if x and y were one-dimensional, you would just get the KR map. But actually, this construction, the KR map is in general it's not really the gradient of something convex. You can say that under some more conditions, every component has that structure. Here, this is on a block sense. You have this exactly. Thank you. So what we're going to consider is this the sequence of OT problems where we're going to look for a map pushing forward rho to the joint of x and y with a cost that is given by the standard Euclidean cost in transporting y and x, but with a scalar parameter weight that I'll call t on the x part. And what can be shown is as you take, if you solve this OT problem for every t, call it the optimal map TT, as t goes to 0, then the map TT converges to a map where the second component has this, is going to be this conditional Brenier map. And so what we can do then is if we choose a particular t small enough, then we can use this to build some estimator for this conditional Brenier map. And we can even say something by a very simple argument that this map is also just related to a standard OT map. So these are maps for each of these maps. TT is a map that's optimal with respect to this rescaled cost, this Euclidean cost with this scaling matrix A that adds a scaling on the second block of variables. And what one can write is that this optimal map TT can be written as taking a map T0, which is optimal with respect to the standard Euclidean costs just by a simple change of variables, and pre and post multiplying by this scaling matrix AT. So if we have some estimator for standard Brenier maps, any known estimator, then we can just plug this in and we'll get an estimator for this rescaled cost. And so the recipe is we're going to, given data from rho and mu, rescale our data by this scaling matrix AT given a particular t, learn an estimator for the Brenier map from our two data samples, and then use this to build an estimator t hat for our OT map. And you can use any estimator here, like the entropic estimator for T0, nearest neighbor estimators like the ones that Tudor talked about on Wednesday, even neural network-based OT approximations. Again, our focus is going to be on the entropic estimator. So just to provide some notation, we're going to solve the entropic problem where we have this standard OT problem plus the entropic penalty will scaled by epsilon. And once we solve that problem, we'll take the conditional expectation to get our of the resulting plan to get our entropic map. and really the thing I want to focus on here is this map is a function which is one can actually extend, not given some training data that we use to estimate these plans via a sinkhorn method. It's going to give us a map that we can use to evaluate at any new input from the source measure. And this is very important because in these conditional sampling problems, you really want to evaluate at a new observation that you haven't seen before. So you really need these maps to generalize to new observations. And these entropic estimators provide a way to do that out of sample. And these days, there's many packages to estimate these maps or solve these sinkhorn problems with on the order of about 10 to the 5 points. So just to provide two results on what we can say about these estimators. The first is that there's, of course, some bias from the choice of the entropic penalty and also this choice of t in the cost. We only really have the convergence to this block triangular map that does exact conditional sampling as t goes to 0 and epsilon goes to 0. So how do you actually choose these parameters in practice? And what we can say at the moment is if we can do some analysis in the Gaussian setting and really show the convergence rates of the map as a function of the parameters epsilon and t to this block triangular transport. In particular, what we can say is that for Gaussian source and target, that the map t epsilon t converges to this block triangular map at the rate of t squared, and with this optimal choice of epsilon also scaling with t squared. And this is really just from decomposing the error in terms of the bias from the entropic part and the bias from choosing this scaling and the cost and trying to balance these two terms optimally. We conjecture that this is in the Gaussian setting, this is probably tight. In the non-Gaussian setting, it's interesting to look at. The second result that we have is about the error of our sample estimator for TT. So without entropic bias, just with this limiting cost. And what we did here to analyze what the estimation sample complexity is again in the Gaussian setting. We considered, just for simplicity here for the slide, I'll point you to the paper for something more general, the transport from, let's say, a standard Gaussian to some general Gaussian. For any t, you can write the estimator in terms of the mean and the covariance, as well as these rescaling matrices. And we can ask how quickly does this estimator, when you plug in a sample mean and a sample covariance, how does it converge to the block triangular transport, which is going to correspond to taking this covariance matrix sigma and building a block Cholesky decomposition of that matrix. And what we can say is that this plug-in estimator, when you have the sample mean and sample covariance with an optimal scaling for the t parameter, does converge at the, in terms of mean squared error for the map, converges at the rate of 1 over n to the 2/3. So slightly slower than the parametric rate. But and that is probably a function of just the analysis. But at least with this kind of scaling, this is also what we are observing in practice. So, and just to really make that visual, so here we did look at exactly these kind of sample complexity results as a function of the number of samples that we're using on the x-axis. On the y-axis, the mean squared error of the estimator. This is with both the choice of the optimal choice of t according to our analysis, scaling with n, and the choice of epsilon for the entropic part. And we're roughly getting this order n to the minus 2/3 rate for the error. You can compare this to at least what Aram and I could do in terms of manual hyperparameter tuning for some neural network-based estimators that are actually converging slightly slower, interestingly. Yes. Thank you. So if you were to go back here to these maps, I do. So the map is converging to this Bloch-Cholesky to a map that is just a function of a Bloch-Cholesky factorization of the covariance. And if you were to just plug in directly the sample estimator for the Bloch-Cholesky factorization, I think you would get the parametric rate n to the -1. Here, I don't have a very satisfying answer for why it's slightly slower. I think it might be just our analysis, but if at least there, I can say confidently that the limiting map would achieve the parametric rate. I can give you the exact details right after the talk. The second example is going back to some of these Bayesian inference problems. So here, what we have is an ODE parameter inference problem. You get to observe trajectories of population dynamics over time, and you want to infer parameters in an ODE that govern the dynamics. In this case, there's 4 parameters. This is a problem where you can actually do run traditional sampling algorithms like Markov chain Monte Carlo. And you could look at the posterior distribution on the right-hand side for the parameters in that model. Alternatively, what we did is we just took the data, which corresponded to 4 parameters, 18 observations in this case, an order of magnitude fewer samples than what's required for MCMC in terms of likelihood evaluations, used our just the parameters that our theory predicts without any additional tuning, and just ran this estimator. It takes on the order of a minute or so to compute the sinkhorn potentials, which is all that's required for the entropic map, and then to sample it very cheaply to get some posterior samples. And you can get a very, I would argue, decent estimate of the correlations between the parameters very cheaply and without any additional hyperparameter tuning. And that's really what I want to convey, that there are definitely estimators for conditional sampling, conditional distributions that can really give state-of-the-art image results. But if we just want simple estimates of things like maybe the correlations in our high-dimensional distribution, then at least here we have a method that's out of the box, can perform quite well. So just to conclude, so we're building estimators for these block triangular maps. We propose an estimator that's tractable based on EOT. And we do have some characterization. It's all in the Gaussian setting. So I'll happily admit that it's limited, but there's a lot of room here to look at some analysis beyond Gaussian settings. One topic that I'm quite interested in is how these estimators might adapt to low dimensional structure in the conditionals. So I have some ideas of how to do that, but I'm also happy to chat with other folks about this. So I'll point you just to the reference, the code, and thank you for your attention.